Hello, hello. We're still waiting. Only 4 students have joined. We're still waiting. Okay, starting now. Good afternoon. Hello, everyone. Can you hear me well? All is fine? Yes. Okay, so before we start, can you tell me, please, if everything is okay with your ongoing projects? So what have you been doing last week? Maybe any questions, suggestions, problems we need to discuss regarding your project work? Not really? Okay, that's fine. So last week You remember we started studying stochastic dynamics of two-dimensional problems in finance. We have had a look at what is correlation between the Brownian motions and at the same time co-integration of the Tarrant terms, and we'll probably have to continue that way and explain how these methods eventually work for pair trading. But unfortunately, or fortunately, there are some real life corrections to our stuff. When our lecture started in January, it was intended to be a course in data mining methods in finance. But today, we are going to discuss, as a slight diversion from our financial path, a different topic. We'll return to our two-dimensional financial models next time in the next lecture. But today, I would really like to introduce you to another type of modeling, which will also show all phases we discussed in the first lecture of how data mining and then data science and modeling work, starting from collection of the raw data, assigning quality labels to this data, so some data are to be trusted, some data are not so much to be trusted, building models out of that, reasoning about the stochastic or maybe not so much stochastic dynamics of the phenomena we're going to study, and producing a meaningful model, calibrating it, and then making this model for using this model for making predictions. The model we are going to talk about is the model of the ongoing COVID-19 outbreak, not financial. How to model the current outbreak. Everyone have heard about it. We are now sitting at homes and we're on remote education sessions. So everyone is talking about the peak of the outbreak or reaching the plateau, whether it has already happened or not. Let's consider this from a strict mathematical standpoint, and we'll...
Professor,
Yes?
we can't see your screen if you are displaying
Not
anything.
yet, not yet. The screen is starting now. Thank you for reminding me.
Okay, just you mentioned that we are going to do co-integration analysis.
We did last time. You remember when we introduced the two-dimensional models with a trend and the volatility structure?
Yes, yes.
Today, we're not going to do that. We'll continue our co-integration models in the next lecture. And today, we are going to talk about the outbreak of the current COVID-19 infection and how to model it. How to model it and how to make predictions about it using the real life data. That's the subject of our lecture today. So let's start. In order to do this modeling properly, we really need to understand, first of all, the data available to us. So before even introducing any formulas, let's see at some data example. As we know, this is the initial phase of any data mining procedure. So we will have a look at what data are available, what can we make of it from the top level, and then we'll proceed about making the mathematical models. So these are the data for the outbreak in Italy, because it is probably the best well-documented case. Starting from the 31st of January this year, when the first two patients were detected, and then continuing on and on and on, including all data up until the most current one. Okay, so what is important to understand about this? Here is the total number of cases, the number of mortalities, and in this diagram there is also a number of mortalities in this brown coloring. The blue color is the number of recoveries, and the red one is the number of still active cases. It is very important to see. The picture is very similar in all national statistics. It would be very much similar actually for, although the actual figures are different, of course, for European countries, for the United States, for China, where it happened originally, for Russia as well. So what is important to understand? When we look at the very initial period, so we see on the 31st of January, the first two cases were reported. And then the number of cases remained unchanged up until the 21st of February. So for 3 weeks, the number of cases unchanged. This period is basically prehistory. It is not the outbreak by itself. This period is not to be modeled. There is nothing that much interesting about it. Then there is a date which we can say, there is a term for that. It is the explosion date. How can we tell the explosion? In the column which depict the number of cases, there is a percentage change day to day, so of the current date compared to the previous date. And the explosion is characterized by a very sharp rise in the number of cases. So you see, it was nearly constant, 2 and then 3 for the previous 3 weeks, and now it is jumping to 20 with, and also on this very day, the first mortality is recorded. So all this data point to the date of the 21st of February and the explosion of the outbreak. So now this outbreak is probably out of control, and it is only a matter of time to get very large number of cases, and unfortunately the increasing number of mortalities. So at the explosion date, the growth is enormous. It is 5 times. You can say whether it is a big deal actually. Okay, there are 3 patients, now 20, not so big. But unfortunately, it is a percentage change which matters. Why we will see in a mathematical model we're going to develop. So a percentage explosion marks the beginning of the outbreak. What was the particular trigger in this case? So why it happened on the 21st of February is still a matter of the debate. There was a football match on the 19th in the European Cup, which some analysts say could have provoked this explosive outbreak. But on the other hand, the delay between the 19th and the 21st is too short for the outbreak to develop, because the incubation period is, the latent period is between 10 and 14 days. So it may have been another event which occurred, let's say, at around the 10th of February, which provoked this major outbreak. So probably not this football, actually. Um, and then we have 567% growth. Then obviously this explosive growth starts to slow down a little bit, but it is still very, very, very high. So in the 20th of February, we are observing the 90%, 53%, and so on, declining, a little bit declining growth, but we're still in the region of just about 50%. On the 1st of March, the growth rate is still 50%, as it was about the 28th of February. So it is still a very fast growth. Then it starts slowing down, and obviously the government measures are coming in place, and so it is not all natural uncontrolled behavior. There are some counteractions. So the government is first starting to introduce isolation in the regions most badly affected, in Lombardy, and from the 9th of March, the government has introduced the nationwide isolation, the state of nationwide isolation, which was further strengthened on the 21st of March. By then, the rate has already fallen to 14%, but it is still quite high. And it continues to fall. And eventually, we can say that basically the turning point when the country has turned the corner was in the early April when the rate declined to 4% something. So it was already in the region of 4% on the 31st of March, definitely as a result of the isolation measures introduced. Then it was a slight increase, but it is probably statistically insignificant, falling again under 4% and continuing to fall now to about 1%. And at this rate, the number of people recovering is already greater than the number of people per day, greater than the number of people catching new infections. So if you see the red boxes, then they are already declining from around the 25th. So slight growth on the 26th, and then again decline for the following 2 days. So now the absolute number of cases is declining. Not just the percentage of growth is declining, but the actual number of cases is declining, which means that the country is firmly on the way to recovery. Italy, I mean, not us, unfortunately. We are not yet. About Russia, we'll analyze the statistics in very detail, and I would like to give it to you as an assignment. We will work out the mathematical methods of dealing with this data and developing the model. So obviously with the typical recovery rate now exceeding the new infections rate and the typical time to recovery, we can say that in Italy and probably in other European countries, including Spain, France, the United Kingdom is in a slightly different position. Then it would probably be over in Western Europe by the end of May, something like that. Not quite sure at all about Russia. We'll need to really see what our mathematical model tells us. So from these descriptive statistics, we can already see important factors. So it is not the absolute number of cases or the absolute number of infections which matter. The most important factor which describes the dynamics of our outbreak is a relative increase, percentage increase of cases day to day, and the associated statistics is about the relative increase in the number of new mortalities and in the number of recoveries. So the first message, as you already know, from what we have discussed in relation to other phenomena, is that it is a relative figures which are important, rather than absolute figures, actually. So let's go to do some kind of modeling from the first very simple model to a more sophisticated one, which would allow us to calibrate it and make some predictions out of it. So, which parameter should we introduce? In the very simple case, but that's a very, very, very simplistic case which we are going to improve. Let's introduce a function, let's say, let me denote it by probably u of t, which is the number of registered cases, the cumulative number of registered cases. So a very simple, very, very, very simple model which we can use for making initial predictions, but it is really by far too simple. What do you think? What kind of dynamics can we impose on this cumulative number of registered cases? Any idea? Well, suppose that there is a given person, just one person, okay? One person interacts with some average number let's say n other persons within a given time delta t. That's a very, very reasonable assumption, right? In the course of our day-to-day activities, we meet some average number of people per day. Let's say when delta t is 1 day. What does it mean, meet? We, before this outbreak, could sit in a classroom, and then we would meet 100 people. We interact with people in the dining room, we interact with people in the course of social interaction, but normally day to day, on average, we would interact with some given number of people. And by the way, this number, especially for students, is not at all small. If you sit in a classroom, then okay, there could be 30, but there could be 150 other people sitting there. Then you are in the canteen, and again, there are probably dozens of other people there. So this n, so if delta t, let's say, is 1 day, then n is of the order of magnitude, let's say in 10 to the power 2, and that's in Annapolis. In, well, in a large city, possibly more, but maybe 10 to 1, but more realistically, we're talking about 10 to the power 2, of the order 100. Probably not 1000, so we should make some reasonable assumptions about this. And then there is a probability P of, unfortunately, infecting another person in this interaction, in the course of interaction, right? Therefore, one person already infected, let's see, already infected, would infect how many people? N times P times delta T, new infections, over delta T, over time delta T, which immediately suggests we don't know what this N exactly is, we don't know exactly what the value of P is, we just do know that one person would infect NP delta T other people over some time delta T, which means that in the simplest case, we are talking about registered cases here. Suppose that all cases become registered. And moreover, suppose that all cases are registered big assumptions immediately. In fact, these assumptions are too simplistic. Um, so we'll say all cases are registered immediately. Then delta x, delta u, which is the increment of the new cases, is if one person over delta t gives rise to np delta t new cases, but there are already u of t people ill and registered, then delta u equals to u times np delta t. Or delta u over delta t is equal to np u, or in terms of concerning the derivatives, obviously we can approximate delta u over delta t at the derivative u dot. By definition, this is du dt equals to, let me call it, let's say, beta u, where beta is np. What is important is that as a very simplistic model, we got this, u dot equals to beta u. Obviously, the solution is to this model. This is a very simple first order ordinary differential equation. solving this is trivial. The solution is exponential. So the epidemic outbreak is always of some exponential kind. So solution u of t would be u0, where u0 is the initial number at time t equal to 0, exponent of beta t. This should be obvious. Currently assuming that beta is a constant. So this constant beta is precisely the daily growth rate. So if we say that the daily growth rate is, let's say, 15%, then we would say beta is 0.15. That's how many new cases, as you see, is created by one infected person per day, where delta t is 1 day, 0.15. In reality, we know that beta is not constant. We have seen that generally beta is overall declining from t equal to 0. By t equal to 0, which time instant, given the example statistics for Italy we have already seen, what would correspond to t equal to 0? Which event? When is this t equal to 0 really happens? Your suggestions, please. Back to this graph. So tell me, please, where is t equal to 0 in this statistics for the purpose of our model? Would it be?
Yes? Date, maybe explosion date, or what was it called like this?
Explosion date. You are absolutely right. T equal to 0 is the explosion date. There is absolutely no point in analyzing, according to this model, any statistics prior to that. It is a different mode with a fixed or almost fixed number of cases. So it is not, the statistics is not applicable. Our model is not applicable to the statistics, and the statistics is not applicable to our model prior to the explosion date. All right. So t equal to 0 is the explosion date. For example, for Italy, it is the 21st of February, 2020. For Russia and the data we are going to use in our analysis in your home assignment are not for Russia as a whole, but for the city of Moscow. And there is a reason for that, because the country is very large and the dynamics is quite different from one region to another. So, for example, the city of Moscow is about reaching the plateau, as we will see in our analysis about now, whereas there are some other regions where, unfortunately, the outbreak is still developing the momentum. So, more specifically, I would say city of Moscow. And we'll see that the corresponding date would be the 1st of March. roughly. Give or take 1 day, but it will be something like that. Okay, so we say beta is declining. If it is declining, then the most simple and natural model we can associate with it is that, again, this was, let's say, equation number 1, the most trivial model. Okay. It is still adequate in the sense that it showed the exponential nature of the process. So, for example, if the number of cases day to day is growing, but the beta is declining, do not worry that much about that. So, for example, the number of new cases today is greater than the number of cases yesterday, of newly recorded cases yesterday. Suppose that. Is it something to worry about? Well, in general, yes. But if you see that your beta rate is declining, then it is already a good thing. The number of absolute cases does not matter that much. Well, it does, because the number of cases actually tests the limits of the national healthcare system of about how to deal with these cases. But if beta is declining rather than being constant, it is already a good thing. Obviously, if we say beta is 0.5 or even larger, then this is very bad. This is the very initial phase of the outbreak. When we say beta is, let's say, in between, declining from, let's say, 0.5 down to, let's say, 0.15, something like mid-phase. Typically, what we have seen by the example of Italy is that it would not decline from 0.5 by itself. Isolation measures are required in order to achieve that. Without isolation measures, it could really happen that beta would be of the order, let's say 0.5, maybe 0.3, but it would still be exceptionally large. But with the advent of isolation measures, it would eventually decline to 0.2, 0.15, which is a mid phase, which is still very much dangerous, and mean that the rate of outbreak is still very high. But now we would say 0.15, 0.5, 0.05 a recovery inside, and 0.05 and eventually negative range, recovery started. Something like that. So a very natural way of modeling this would be a linear model. So beta is beta 0, which corresponds to the initial outbreak, minus some kind of constant beta 1 times t. For reliability of our model, I would recommend not to use the very explosion date as t equal to 0, but maybe move a little bit further beyond it. Because, for example, if we look at this, and we say we model our delta by a linear function, it is simply far too high at 567% and so on within the initial 3 days to model this linearly. A linear decline, some kind of linear decline, probably starts from the 24th of February in this case. So I would recommend, if we use a linear model for the decline of beta, is to take maybe some initial point which would fit much better in this linear decline. So let's say for t, in this case, for t equal to 0, in this case, may select a more reasonable date for t equal to 0. Otherwise, beta 0 is going to be far too high, and the model is not applicable. So it was not a linear decline in the first few days. In the first few days, we would say if this is a beta of t, of what we have seen, not the number of cases, but the rate. So after the explosion, the rate drops very, very significantly initially, and then it starts dropping more or less linearly. So then for t0, we t equal to 0, we select maybe this date by moving our axis. This phase of a very high initial explosive rate and then dropping to on some more reasonable rate is, in this case, beyond our analysis. So we move the 0 point by a few days. For beta 0. In this case, it would be not the 21st, but let's say the 24th of February 2020. So apply your reason and your judgment. But from that point on, the linear model works quite well. So what do we get? We get u dot equals to beta 0 minus beta 1t times u. That's the new ordinary differential equation which we need to solve in order to get the dynamics. By the way, in the first equation which we got, we just have an exponential growth, which means that the number of cases is increasing and increasing and increasing and never stopping. So obviously it is a very simplistic and very pessimistic model. With this model, we can now see the end of the outbreak in sight. So how do we solve this, this equation? U dot equals to beta 0 minus beta 1t times u. All of you have had the course of ordinary differential equations in your second year. So please recall, what do we do for equations of this type? Any ideas? No ideas. A very important message. It is separable. Yes. Vladislav says it is separable. It is the absolutely right remark. We can solve this equation by separation of variables. More precisely, we say replacing u dot by du dt we say it is same right hand side, or du divided by u equals to beta 0 minus beta 1 t dt. We achieved separation of variables. The left hand side is a function of u only, the right hand side is a function of t only. Now we say that because there are identical differential expressions, only one depending on u and the other one depending on t, in the left hand side and in the right hand side, then integrals of them should also be equal up to a constant. Therefore, integrating the left hand side du over u from the initial number of cases u0, let me use, that's a good way to rename the dummy integration variable so that it is not confused with the upper limit of integration, from u0 to the current u would be equal to the integral from t0 is 0 to the current t of beta 0 minus beta 1 dummy t dt, from which we get, obviously, that the log of u over u0 is equal to beta 0 t minus beta 1 t squared halved, right? And we get u of t equal to u0 exponent of factoring out t, exponent of t beta 0 minus beta 1 halved times t. That's our equation number 2. It is a much more realistic setup, as you can see. And what does it mean? It means that at some point, our function u of t will start decreasing. The total number of cases, in this case, will start decreasing. And we can really say when it happens. It happens when the exponent becomes negative. So, when beta 0 minus beta 1 half t becomes negative, okay, or equivalently t becomes greater than 2 times beta 0 over beta 1, we would have u of t decreasing. The new cases still occur, but the number of new cases is less than the number of recoveries in this case, and therefore the total, what is u of t? This is the total number of registered, that's a good point. U of t, if it is a total number of registered cases, then it wouldn't become, it wouldn't be decreasing. We initially said that u of t is the total number of registered cases. It really depends. If a person recovers or unfortunately the person has died, then they may be excluded from the total number of registered cases, and then we have this reasonable behavior. But if U of t is the total number of cumulative number of recorded cases, then it may not decrease. So there is a difference. So total cumulative recorded cases what do we see? We see some initial explosion time t equal to 0. Then there is an exponential growth. Then there is an inflection point. And then eventually we would say it must reach some kind of asymptotic maximum. But the total number of active cases of people who are still ill I wouldn't say total, number of active cases. Number of active cases. It will behave in a different way. So again, initially the total number of active cases is about the same as the number of recorded cases. People do not recover, but unfortunately some people die as a result. Then there is a possible plateau and then exponential decreasing of the total number of active cases. So equation 2, which we have derived, it is more about this. So in this case, U of t is the total number of active cases rather than recorded cases, because without that we wouldn't have would have a horizontal asymptote rather than the number of cases declining. So basically, the model 2, although it is entirely reasonable, it is not for what we originally developed it for. It is not for the cumulative U of t. So not really valid for U of t. For U of t, we would have something. Would have to have something like this. But valid for the number of active cases. So what can we make of it? Both models, which we have developed, are not valid for the total number of recorded cases. The first one, equation 1, would correspond to eventually unlimited exponential growth of the cases. This is fortunately, well, let's hope, not a realistic situation. So equation 1 would be like this. Or repeating it here, that's what equation 1 would do. Equation 2 is this, which is valid for the total number of active cases, but the curve for the total number of cumulative recorded cases is neither 1 nor 2. It is something different, which means that the models we have developed so far are approximations only, and this is completely normal. What I would like to tell you is that it is perfectly okay to start with a very simple model, explore its properties, and then see whether this model is adequately describing all phases of the phenomena we are currently modeling. So, as turned out, none of these models is entirely accurate. So what? Let us then develop a more sophisticated framework, which would allow us to accurately model all those phenomena. In this case, we will need several functions rather than just one function. Let's, after familiarizing ourselves with possible models and their shortcomings, let's produce a more accurate model. Okay? Trying to take into account all factors we can think of as being meaningful and reasonable. So once again, we will use this u of t as the cumulative number of recorded cases. Okay, but that's not the primary variable we actually need. Why? Because first of all, we need to distinguish between this cumulative number of recorded cases and the number of cases which expired, either due to recovery or unfortunately due to the death of the patient. And also very importantly is because the number of recorded cases might not be the actual number of real cases. Many cases, maybe 50%, as some statistics suggest, maybe more than 50%, are simply not recorded because they either misdiagnosed or they come without any symptoms at all. So the cumulative number of recorded cases is not the primary variable we want. For the primary variable, what would you suggest for the primary variable? Better than the cumulative number of recorded cases. Let's say for the primary variable, we will use the actual number, the real number of active cases. X of t, a real number of active cases. Unfortunately, this real number of active cases is unobservable. So this is unobservable internal state variable of our model. But it is a very important internal state variable from which we derive other variables and eventually construct a system of differential equations which allows us to model this phenomena with high accuracy. So, okay, real number of active cases at time t. In this case, by the way, t0 would not be like in Italy on the 21st of February, because on the 21st of February we get explosion of recorded cases. But those cases were latent for quite a while. So t0, instead of moving forward, would be moved backward in this case. Okay. What can we say about the dynamics of the actual of the real number of active cases? First of all, what about the rate of increasing of x of t? It would be in a similar way exponential, because those people with active cases, they continue to, unfortunately, infect other people. But let's make a simple assumption that if the case is already recorded, the person is put into either home isolation or in a hospital, so that person doesn't continue to infect other people. So we would have the situation with x of t. Um, okay, apart from x of t, u of t is a cumulative number of recorded cases. Okay. We would say out of this, there is also a current real number of active cases currently active. There is also some number of recorded active cases. This is not u of t because u of t is the total number of cumulative number of recorded cases. It is not really that much useful variable. So let's say y of t is recorded instead of real, recorded number of active cases. What is the relationship between x of t and y of t? Obviously, there are some active cases which are undetected, so y of t is less than x of t. As a very initial approximation, we can say that there is some proportionality relation between them. So y of t is equal to some detection coefficient. Let me denote it by alpha. Detection coefficient times x of t. Alpha is less than 1. So at each and every given t, we have x of t real ongoing cases, but some of them go unreported. So that's a kind of detection coefficient. In this case, latent undetected cases are 1 minus alpha times x of t. And it is these basically latent patients which give rise to new infections. Those who have already been recorded are put in isolation and hopefully do not produce any meaningful number of new cases. Therefore, we can say that the new cases x dot, which is the growth rate of the new cases, is again some coefficient beta, which at this moment I do not expect to be a linearly declining function of time. For the moment, we can even assume that it is a constant. Later on, they can be made functions of time or even of our x, y, and other variables. But for the moment, we would say x dot equals to the coefficient beta times the number of undetected cases, which is 1 minus alpha x of t. But still, we would have in that case that x dot is proportional to x of t with some other coefficient. So beta times 1 minus alpha, let me denote it by, let's say, beta tilde, and we still have basically same law of x dot being equal to beta tilde times x of t. We don't know this coefficient yet. It is a product of beta times 1 minus alpha, but a priori, we don't have the values for beta or for 1 minus alpha. Just this, okay? And this number of real active cases is not known to us. We can't observe it directly. What we can observe, the number of detected cases. Basically y of t, recorded number of active cases. We say here that y of t initially, as we said, is proportional to x of t. Not exactly. Let's see what happens. So at some point in the past, which I denote by, let's say, T1, a person got infected. Then there is a latent period. Whether within this latent period the condition is detected really depends on whether mass testing of the population is carried out in order to reveal the latent cases. We would say, with one exception, in South Korea, this testing was really able to detect latent cases before clinical symptoms were out. But even then, the latent period still exists. It is just shorter because obviously it is not possible to detect the condition right on the day of infection. You are going to be tested maybe in 1 day, maybe in 5 days. Then some time is required for the test to be processed. There is still latent period. So at some time T2, the case is recorded. How? Either via clinical symptoms, or by test results. By test results. Let us denote this interval from the infection time to the manifestation time. So this is manifestation time. We will denote this time interval by tau1. Okay? By tau1. Then when this manifestation time, within this time tau1, new cases can be produced by this person. At manifestation time T2, the person is hospitalized or ordered to stay at home, so they stop infecting others. Then there are two possible outcomes. From the manifestation time, there is a time tau2, which may unfortunately lead to the death of the person. Or from that, there is a longer time typically longer time, which we say, and yes, this is T3. There is a longer time to the event which we denote T4, and this time is TOR3, which is, what is here T4? Recovery. Okay? So, from that point, let's see what the equations for our dynamics are going to be. This TOR1, TOR2, and TOR3 are parameters of our model, which we may or may not know a priori. Typically, from the clinical examples, we do know that, well, TOR1 is, it really depends on the quality and the number of screenings in place. So the clinical symptoms, if testing is not conducted earlier, the clinical symptoms would typically occur within, let's say, 10, 14 days. In case of very extensive testing, TOR1 is less than that. We can roughly say that it is 10 days, something like this. Although we do know approximate values for these parameters, it would be a good idea to actually calibrate these parameters later on based on our actual model. TOR2, from the occurrence of symptoms from detection to a crisis point, which may or may not lead to the death of the patient, is something like 5-8 days. And recovery, again, from the occurrence of symptoms to the full recovery when the patient is tested negative, TOR3, is probably 14 to 21 days. Again, we'll need to calibrate this value, the average value of TOR2 and TOR3, based on our models. So then what happens? Let's write down, based on this time diagram, our equations once again. I would put a question mark here because what we have done initially is based on this y of t equal to alpha x of t relationship, which might be reasonable, but it is not the whole truth. Okay. Suppose that we are at time t now. Okay. Consider that's now. Consider what is happening. We will consider also, and we have x of t, which is the number of active cases right now. We'll try to finally create the dynamic equation for this number of active cases. So, apart from this t now, we'll consider some other times. We'll consider t minus TOR2. That's an interesting, okay, we have TOR1, and then from TOR1 we have this interval of TOR2. So what I'm trying to make, actually, what would be my idea is I want to develop the model for x dot of t. Okay, so first of all, the number of currently active cases at the time t. So first of all, how would this number increase and decrease? First of all, the number of active cases now at time t, unfortunately, decreases due to death of people. So there is a certain mortality rate which I denote by gamma, mortality rate. Which people would die with this mortality rate gamma now at time t? It's basically the mortality rate is typically measured relative to the number of people admitted to the hospital, but we can say that there is also a mortality rate inherent in the model relative to the number of infections. So it is minus gamma multiplied by what? So basically, let's say the mortality rate is the probability for a person to die, for a person already known to be infected, to die per just to die of this infection. Okay, this probability needs to be applied to which number of people? So, okay, a person which got an infection dies with the probability gamma. Okay? To which people, even to make it a little bit more clear for you, I may replace the dot with deltas, but okay, to which people this gamma rate would apply if we are observing this t now? To the people who got ill at which point? Long time ago. In order to die now, first of all, the time tau1 need to pass from the onset of infection to a clinically developed stage, and then from that clinically developed stage to, unfortunately, the actual tragic event. So x dot of t equals to minus gamma times the rate of infection, x dot, the rate of new infections, which occurred long time ago, t minus tau1 minus tau2. This formula is not complete yet, but I would like you to understand this very precisely. So at long time ago, within the interval delta t, that number of person x dot of t minus t1 minus t2 times delta t got infected. All those people progress up until time t, and a certain proportion of them, gamma, died. So the death rate now is connected to the infection rate long time ago. Okay. Now, let's say if gamma is a mortality rate, so for a person who have died, there is a probability of gamma, for the person who got infected, there is a probability gamma to die. Then for an infected person, there are only effectively two outcomes. Either you die, unfortunately, or you recover. Therefore, 1 minus gamma is the recovery rate. So the probability that the person who got infection will effectively, eventually recover. So the current number of active cases is reduced also due to recovery with the coefficient 1 minus gamma. X dot, again infection rate, but for recovery longer time is required. So it is T minus tau 3, which is the time required for recovery, minus tau 1. Okay? So these two factors contribute to the decay in the number of cases. Now, which factors contribute to the increase in the number of cases? New infections, right? The new infections are produced by all people who are infected but not but have not recovered by now. Sorry, but have not been detected by now. So here there is some kind of infection rate better. Times let us denote by I would say y tilde of t. Because these infections, new infections, they do occur right now, where y tilde of t is the number of undetected active but undetected cases. Just a second. Hello? Hello, Justin. I am in the middle of lecturing now, so would it be possible if we talk shortly afterwards? Okay. Okay, thank you. Thanks. Active but undetected cases, y of t. So in order to complete this equation, we need to determine what the number of active but undetected cases is. Okay? So what can we say about this y of t? The number of active but undetected cases. Let's say that active but undetected cases are simply all cases from X which occurred not which occurred more or less recently. All right. So, what is the dynamics of this y of t? So any case which has occurred, for example, before, which occurred not more recently than t minus tau 1. So if the case occurred before, later than then, it is yet undetected. So, but these are different quantities. So we may have, for example, x of t minus tau1, that was some number of cases. But then the number of cases would be increasing, and at this current moment, there is a current number of cases x of t. So, which cases are definitely detected? Definitely detected are cases which occurred prior to time tau1. Okay? All cases from tau1, the t minus tau1, are undetected. Therefore, we can say that if the current number of cases is x of t, and that was the previous number of cases at the time t minus tau1, these cases are all detected by now, and the difference between them is the number of undetected cases. So we can say that y of t is the current number of cases, yes, but fortunately, it is reduced by the number of cases which are isolated by now. And isolated by now are all, well, not necessarily all, because there could be, unfortunately not, because there could be asymptomatic cases. So minus number of isolated cases. And the number of isolated cases is the number of cases we have seen at t minus tau1 multiplied by the detection rate. So we need yet another parameter, delta, which is detection rate. Because unfortunately, some cases can be completely asymptomatic and not, in this case, or might not be revealed by testing. So minus delta times x of tau minus t1. Here we are. So now we got a mathematical model, more or less reasonable one, which describes the dynamics of our outbreak. So once again, let me write it down. We get x dot at time t equals to the infection rate these people unfortunately produce, the infection rate beta, applied to undetected cases, all currently running cases, minus cases occurred previously, but unfortunately also multiplied by the detection coefficient delta. It would be nice if delta is equal to 1, but it is not. X of t minus tau1 okay, minus the death rate, unfortunately, x dot for the people who got infected, and minus 1 minus gamma x dot of t minus tau1 minus tau3. What is this? We have arrived at this equation, which is an ordinary differential equation, but not quite a familiar one. Can you tell me, please, what is the difference between the equation we have obtained and the ordinary differential equations you have seen previously, for example, in your ODE course in the second year? There is something different, fundamentally different here. It is first order. We only have first order derivatives, right? X dot, which is a derivative with respect to time. But you see that the right-hand side of this equation, typically, what is your first order ODE? What is the structure of your first order ODE? Even if it is not resolved with respect to the variable, the structure would be f of x dot x and t equals to 0 if unresolved with respect to the variable, or resolved would be x dot being some function of x and t, which means x dot at time t is a function of x again at same time t and t itself. But here, x dot is a function of x at a different time. You see, x of t minus tau 1. Here, it also depends on x dot, like in this first form, f of x dot xt equal to 0. But this x dot is again applied not to the current time t, but to the previous instant, t minus tau 1 minus tau 2. And finally here, x dot is applied to yet another different time. So it is not quite an ordinary differential equation. It is so-called an ordinary differential equation with deviating arguments. Why deviating arguments? Because the time is not always t. It is t minus tau 1 here, it is t minus tau 1 minus tau 2 here, and so on. Solving these equations with deviating arguments in order to calibrate our model is a more difficult procedure. There are some analytical ways of how this can be done, but it quickly becomes far too difficult actually to do it analytically. To that end, next time we will develop a numerical procedure which will allow us to deal with this type of models. And one final remark, okay, we can't really calibrate this model by itself. There are some unknown parameters, beta, delta, gamma, and those delays. We can't really calibrate this model because x of t is not directly observable. In order to calibrate the model and to determine the actual parameters, we really need to derive observable values out of it. So now let's see, what are the observable values? X of t, unobservable. What is observable? First of all, unfortunately, the death rate is observable. Every day we know how many people have died. And actually, this is by far the most reliable parameter. So directly observable, and what is the death rate? The death rate is this one. It is gamma times x dot of a previous time, t minus tau 1 minus tau2. Let me denote it by d of t, by the death rate. This is observable. Okay. Recovery rate is observable. We know how many people are discharged from the hospital and declared clear of symptoms every day. That we do know. 1 minus gamma, this term, times x dot of t minus tau1 minus tau3, which I denote by r of t, recovery rate, is as well observable. There might be some other parameters observable, like, for example, the total number of people in the population who developed immunity due to serological tests to the disease, and that's why we can estimate the total number of cases per, let's say, 1 million of population. But this data may or may not be available. The total number of active recorded cases can also be derived from this, but okay, and yes, so the total number of active recorded cases, number of active cases, we know what it is. It is precisely this term, actually. It is let's say A of t, delta times x of t minus tau1, which is the latency period. This is A of t. So interestingly, you see this d of t, r of t, and A of t, they're all observed as of today, for example. But in fact, they're all connected to our internal hidden variable x only at different times. D of t and r of t are actually x derivatives rather than the values of x. And they refer to the previous values at t minus tau1 minus tau2, t minus tau1 minus tau3, where the current number of active cases, recorded active cases, number of recorded active cases, is the detection rate applied to the number of total cases observed previously, because some of them are still undetected. What we will probably do next time, using the actual statistics available for, let's say, the city of Moscow, and using the methods for integrating, numerical methods for integrating ordinary differential equations, we'll develop, I think we'll do it in your labs, we'll develop a method to calibrate this model and to make predictions about the outcome and the decay of this epidemic. Thank you. Any questions, please? Thank you. We are done.